Welcome to the lectures on high voltage engineering. In this lecture video, we are going to discuss a single stage high voltage impulse generator. Here in this lecture video, we are going to discuss the circuit detail of this high voltage impulse generator. We will be discussing the working principle, and we will also be discussing the practical knowledge about this single stage high voltage impulse generator. What is an impulse voltage? What is a switching impulse voltage? What is a lightning impulse voltage? What is the difference between them? We have covered these topics in our previous video lecture, and let me revise the concept of an impulse high voltage. Although we have covered this concept in detail in our previous video lecture, impulse voltage or high voltage impulse is a type of high voltage which appears in our electric power system. Now, impulse voltage waveform looks like this. The voltage rises immediately to the peak value and then decays. This is the basic waveform of an impulse voltage. Now, this impulse voltage, it appears in our electric power systems. Now, what is meant by electric power systems? Electric power system means that we have the generation, we have the transmission system, transmission lines, and then we have the distribution system. So in this electric power system, such type of impulse voltages appear. Now, these impulse voltages are not the normal voltages, but they are produced due to several reasons. Like, if the impulse voltage is produced due to the lightning strike on the transmission line, then it is known as lightning impulse voltage. And you will observe that in the transmission line, in the transmission level voltages, you will upon the lightning strike, you will observe a high impulse voltage. Now, impulse voltage is a type of voltage which is in the form of several kilovolts, and it may also be in the in megavolts. So such type of impulse voltages appear in our system, and obviously why it is dangerous? It is dangerous for the electric power systems. Like, it is if you have a bus bar, and bus bar is supported on the insulators. Similarly, conductors are also supported on the insulators. Now, bus bar is intended to operate, let's say intended to operate on 220 kilovolts, but this high voltage impulse of around 700 kilovolt, if there is a lightning strike somewhere on the bus bar, then the high voltage will also appear across this insulator. So this insulator may damage as a result of this high voltage impulse. And so why we are interested in studying this circuit? Because we want to test these insulators. We want to test the cable insulators, so that against these impulses which occur in the system, we want to see that either these insulators can sustain such type of impulse voltages which appear in our actual power system or not. For that purpose, we need to generate such impulse voltages across our insulators in our high voltage testing labs, and we apply such impulse voltages across these test objects so that we can check their reliability upon these impulse voltages. Now, impulse voltages can be of two types, either due to the lightning impulse, or in the system impulse voltages also appear due to the switching. Now, what is meant by switching? Let's say due to the some fault or sudden tripping of the load or you remove a load, you turn on or turn off a heavy load on the power system. As a result of those stored energies in our inductive loads, we get the impulse voltages in our transmission lines, in our transmission line conductors. And the impulse voltages which result through the switching are known as the switching impulse voltage, and this type of circuit can create lightning impulse voltages as well as the switching impulse voltages. This is a complete circuit of an impulse voltage generator. We will be understanding each and every component, and we will look for which components play their role in which type of thing, like impulse voltage, which is the impulse voltage, which is the lightning impulse voltage, it rises quickly and decays quickly. But the impulse voltage which is due to the switching, that impulse voltage rises, takes some greater time as compared to the impulse voltage which is due to the lightning strike, and then decays in a greater time as compared to the impulse voltage of the lightning strike. So switching impulse voltage contains more area under the work. It means that the switching impulse voltage has more energy in it, and more is the energy, the more insulator should be able to sustain such type of abnormal rise in the voltage. In a nutshell, an impulse voltage in a power system can be defined as an abnormal rise in the working voltage, and this impulse voltage has two things. One is its rise time, and another is its fall time. Okay, so and impulse voltages can also be in the form of oscillatory waveform, like it is in this way. It can be in the form of oscillations. So such type of impulse voltages also appear in the circuit as a result of the switching impulses. So what we are going to do, we are interested in generating such type of impulse voltage in our high voltage testing labs, such that we can test the insulators. So here is the circuit. Now in this circuit you can observe there are several inductors and capacitors and resistors. Looking on the key concepts, a resistance is meant to control or to limit the current flow. Then we have inductors and capacitors. Now inductors and capacitors are meant to store the energy. Okay, so it means that there are energy storage elements in this circuit, the inductor, the capacitors, okay, and the resistors are meant to limit the amount of current flow. One thing here is the G is represented, this is the spark gap. Now this is the spark gap. This spark gap is meant to break over, that is, when there will be sufficient charge in this capacitor, then this spark gap will able to break. Okay, so let us see one by one about the components. This spark gap is also known as the voltage sensing switch. You can say it the voltage sensing switch, because once this capacitor is about to charge, when the voltage across this capacitor is sufficient enough so that it is able to cause the breakdown of the air between the gap, then the spark gap will break and the current will flow. So this spark gap, you can see that it is like a voltage sensing switch, a type of switch which will turn on when the voltage across this gap is more than the breakdown voltage of the set parameter. Like you adjust this spark gap so that you know that whenever the voltage will be more, then the spark gap will be will break down and the current, and it will conduct. Spark gap will only conduct when there is sufficient charge stored here. Okay, then there are other resistors like this R1. This is also known as the damping resistor. Now why it is known as damping resistor? Because it is actually controlling the current flow. Then these resistors R2 and R4. These resistors R2 and R4 are used to adjust wave front and wave tail. What is mean by wave front and wave tail? The wave front, the time required by a waveform to reach its peak value, this is known as wave front time, and this is wave tail. You can see that in the lightning impulse voltage, there the wave front is small and the wave tail is also small, while in switching impulse voltage the wave front is large and the wave tail is also large. So these resistors are meant to adjust these wave front and wave tail. And then we have also the combination of resistor and inductor here. Now these are the additional elements which are meant to control the wave shape. What does it mean? This is a type of wave shape which has oscillations. This is a type of wave shape which doesn't have the oscillations. So this inductor play a role in creating these oscillations in the circuit. Now what is this? This is actually the test object which is under this red box. Now a test object, obviously what is a test object? It can be an insulator. So in a test object you have capacitor and inductor. Now test objects typically behave as the capacitive loads because they have very low power dissipation, and the behavior of that test object when we apply the high voltage across it. Test objects, like what are your test objects? The insulators, they behave as normally the capacitors. So this is basically what this is, the test object or the insulator under test. It is indeed more capacitive in nature. Normally test objects are more capacitive in nature. So this is the complete circuit. It contains energy storage elements, it contains the additional elements to control the wave shape, and R3 and R4 to adjust the wave front and wave tail, and this is the damping resistor, also known as the charging resistor, and here inductor as well. This also plays its role in storing the energy that helps us in creating the high voltage impulse. Okay, so in this circuit you might be thinking that this resistor R1 is placed here. Well, this resistor, you know why this resistor is placed here? This resistor is meant to limit the amount of current flowing in the capacitor. Now one question may be asked that if there is a DC supply in a kilovolts here, and then also the potential difference will be across this spark gap. So in some other textbooks, and I also agree with that, this damping resistor must not be here in this place. This damping resistor must be here. Okay, so I am also because in one of the popular textbook they placed a damping resistor here, but in other textbook they placed here, and I also agree that this damping resistor R1 must be placed here instead of placing it here. Why? Because once at start this capacitor has to charge. Now when the capacitor is charging, a lot of voltage is dropped here, so this voltage sensing switch will not conduct, or there will be no such spark over, because high voltage is dropped here. But once the current flow has been stopped, now this capacitor has the voltage almost equivalent to this supply voltage. Now this spark gap will break. As soon as the spark gap will break, this capacitor will shift its energy across into this capacitor, and current will also flow into this inductor element as well. Now what happens? Now there is an inductor and there is the capacitor. What happens? These resistors are much smaller. They becomes in, you can say the current the energy starts to exchange between this inductor and capacitor. And also this is a test object, and the voltage although will be appearing here, but it will not be there will be no such breakdown, because the voltage is typically low at that time. What happens again? This capacitor is again charging and it will again discharge. Then what happens? Due to continuous charging and discharging and the energy exchanges between these energy storage elements, and this spark gap breaks over again and again, and eventually we get to the higher voltage across this test object, and this test object tends to break down. Okay, so I think we have pretty much explained the working of this circuit, and this is the complete circuit of the high voltage impulse generator. Now which type of circuits are commonly used in our applications for the impulse generation circuit? This is the complete circuit, but it is not necessary that you go for this complete circuit. This circuit can also be minimized or modified or simplified to an extent depending on the type of waveform you require. So we have some other several type of sub-circuits which play the role similar to this single stage impulse voltage, or in fact you can say that the circuits which I am going to draw now, they are derived from this main circuit. Now what are those circuits? Let's see them. So here are the modified versions of the single stage impulse generators, and they are typically sufficient for your lab work or for your practical demonstration. Now you can see here they are the modified circuits, and you can see here is this is R1 and C1. This is the damping resistance, and this is the generating capacitor. Similarly, this also known as the current limiting resistance, R1, C1, they are common now. They are common. This part is common here, and here we have the spark gap. What's next in the modification is here you have an inductor and the resistor here. Let's say this is, let us name it as well. This is R2. Okay, we name it also R2, R3, and let's name it R2, rename it to R3, R2, R3, and R4. So we have the spark gaps here. You can see these are the spark gaps, and they break down when the voltage across this gap is greater than the breakdown voltage, and they are adjustable. Spark gaps can also be broken down using using some switch there as well, and we will be studying a trigatron method of breaking the spark gap soon in our lectures. And so here we have inductor. It means that the waveform which you will be having on the output it will be having some oscillations in it. There will be an oscillatory impulse voltage generated here. Here there are only resistors and capacitors, so there will be the normal impulse voltage here without any oscillations. It may be rising and then falling down. Such type of impulse voltage will be generated here. Similarly, this circuit is as well here. This is used for the simple impulse voltage and also for the simpler impulse voltage. This type of circuit is used for generating an impulse voltage which has oscillations in it. And what is the difference between these circuits? There are advantages of wave front and wave tail time control adjustments. Like this circuit provides you better controllability over the wave shape. You can have more flexible control over the wave front and wave tail time. Anyhow, any of these circuits may be used, or either you can also use the complex circuit which we have discussed before. Now let us discuss some other practical parameters. What you can do, you can before performing them the practical, you can make these circuits in Simulink or any electrical simulation software, and then you can also observe the output there. You can add in the spark gaps or the manual or time switches here, and you can observe the output wave forms of these circuits in MATLAB or Simulink software, as well as you can also use some other softwares, but this is most recommended software for such simulations. Now let's come out the voltage equation, the output voltage equation, which the output voltage which we will get, the maximum output voltage which we can get through any of these circuits, or either the main circuit we have just discussed. The output voltage is equal to capital this output voltage. This is the time dependent, obviously. It is equal to output voltage equal to input voltage, but 1 minus 4 L by C R square to the power 1 by 2, that is, this is the square root. Well, how this equation is derived? This equation is derived using the concepts of network analysis. Well, it is not your concern to derive this equation at this stage. We have to understand this equation, and we have to do the practical demonstration of the high voltage generation, because you know how it can be derived. You have studied those concepts already. So V is the applied voltage, the input voltage. L, now what is L? L here is the equivalent inductance of the circuit. And what is C here? C is the equivalent capacitance of the circuit. And what is R? R is actually equivalent resistance of the circuit. So you know the rules and theorems of network analysis and electric circuit analysis. You can find out the equivalent inductances, you can find out the equivalent capacitance, you can find out the equivalent resistance of such circuits. So this is the output voltage of this circuit. This is the theoretical output voltage. Obviously, practically there are some other voltage drops across the self inductances and some other parameters, but this is the voltage output voltage equation of the circuit. Okay, now this output voltage, this is not this is my mistake, this is not time dependent. This is actually this equation is telling you the maximum voltage, the peak voltage, the peak value of the impulse voltage which can be reached. So this is the equation for the output voltage. Now let's discuss about the performance parameters, like what is the efficiency of the impulse voltage generator which we have been using. To determine the efficiency, you have the formula N is equal to 1 divided by 1 plus C2 by C1. Now what is C2 and what is C1? Now C1 defines the capacitor which is in action during the charging time. Now C1, you can see this is the capacitor C1. Now this capacitor C1 is active when this circuit is charging, that is during charging action. And what is C2? C2 is the capacitance of the circuit during this charging action. During this charging action, C2 is the capacitance of the circuit during the discharging action. And so in this way you can find out the efficiency. Another term which is also important is about the transfer of energy. The transfer of energy, that is the impulse circuit can transfer how much of energy. It is in watt. It is equal to 1 by 2 C1 and V output square. C1 is this capacitance, C1 the capacitance which is active during charging action, and V out it is the maximum or peak output voltage of the impulse voltage peak. So this much amount of energy is transferred where? To the test object. Okay, and how to select this capacitor? This is an important thing. How you should calculate the value of the charging capacitance. How much should be the value of the capacitance chosen? That is given by a simple formula. How these formulas are calculated or derived, it is none of your concern. So the selection of capacitor C1 is equal to MVA into 10 raised to power 8 divided by ZV square, and it is equal to, and it has a unit of farads. Now what is MVA? The megavolt ampere. Okay, it determines this is actually the capacity of, or you can say the capacity of DC supply. M is the mega voltage and ampere. The voltage you have here and the amperes you have here. Don't confuse it with the AC value, the apparent power. This is not the apparent power. This is actually the you can say the input power, the power available from your DC source. Okay, and what is V? V is the input voltage. And what is Z? Z is the equivalent impedance of circuit. Now what is meant by equivalent impedance of the circuit? While calculating the Z, you ignore this capacitance. You look here, the equivalent impedance. The equivalent impedance of the circuit is what? Okay, so in this way you choose the capacitance value C1. So here we are up with the we are done with the single stage high voltage impulse generators, and if you are interested in multi-stage, then you have the more another practical approach, that is the Marx generators. which are the volt, or you can use the Marx generator, that is the voltage doubler circuit. Either you can use Cockcroft or the Marx generators are used if you are interested in generating more high voltage impulse voltages. So this is the single stage impulse voltage, and for multi-stage you go for the Marx generator. So here we are going to end up this video lecture, and we will be meeting you with the new topic in the next video lecture.